Okay, first of all, I would like to thank the organizer for inviting me here. It's a pleasure for me to speak here, mainly because there are a lot of specialists in the field here, and it's a pleasure to explain to experts your result. In fact, what I'm going to explain is a method, rather method than result, because only if you really knew result, you could derive by this way, but there is a very big advantage of the methods that almost all known results about beta matrix model you can obtain using these methods. And general conclusion from the methods is that if you could do something for Gaussian potential with a small perturbation, then you could transform the same result, whatever you want. Rigidity, local semicircle, whatever you want, you can transform immediately to the case when you have general potential. So let me start from the definition of the model. Just standard thing, you have distribution. What is a matrix, beta matrix model? Just a definition which have two parameters, one a functional, one is function v, and another one, and v is real valued function growing faster than 2 logarithm at infinity, and another parameter is beta, is a real parameter. So this is normalizing factor, normally called partition function of the model. And why it's matrix model? Because for beta equal 1, 2, and 4, it is a joint eigenvalue distribution of real symmetric Hermitian and symplectic matrix model. Few more definition. Okay, the expectation. I will denote by expectation with angle the expectation with respect to my probability measure, and also there are correlation function or marginal density when you have this distribution, and just integrate with respect to extra variables. If you want to know correlation function of lambda 1 and so on, lambda n, you should integrate with respect to lambda m plus 1 and so on. And just convenient notation which I will use is a linear, the first one for some special kind of function h. If you have one variable function h and consider the sum of h of lambda j, this is called normally linear eigenvalue statistic, and the special case of linear eigenvalue statistic is this function when you take as a function h the indicator of some interval. And of course, if you consider this function for any interval delta, you obtain the number of points lambda j in this interval. So n of lambda is the number of points in your interval. So normally when you study random matrices, there are global and local regime. And main problems of the global regime, first of all, it's the convergence of eigenvalue distribution, or in these terms, the convergence weak limit of the first correlation function. Then the second, it's weak limits of the other correlation function. Normally they are factorized, and the speed of this factorization is also a very interesting question. Again, the next one is large deviation type bounds for the correlation function, and more refined questions about generating functional. If you would like to study, for example, CLT for linear eigenvalue statistics, then it is natural to study the generating functional or Laplace transform of this linear eigenvalue statistic. And here we are lucky because we can write this generating functional like a ratio of two partition function, just v minus 1 over nh, because there is parameter v here, and the ratio with the standard partition function. And the last question, which I know from global regime. Okay, there is also CLT in some intermediate regime, but I will not stop today on this question. And also very important question, there is expansion of log z, of log of partition function with respect to n minus 1. And if, for example, the first, the second, and the third question you should consider independently, but for fourth and fifth, the method is okay and well much better than known before methods. Okay, and as for the problem of local regime, of course, the main problem of local regime is the universality, and there are a few kinds of universality. First one is the universality of local eigenvalue statistic, which is the same as the universality of correlation function, which means that if you consider the m's correlation function and do normalization, okay, rescaling of this, and consider this, sorry, I forgot to say, you take lambda 0. If we speak about the bulk case, then you have to take lambda 0 inside the bulk and consider the correlation function in the neighborhood of this point lambda 0, and you should make a scaling, and then this function as a function of S1 and so on, Sm, should be universal. This is the universality of correlation function. And the universality of the gap probability is just, okay, what is the gap probability? Gap probability is probability to find some interval empty of the eigenvalues. I should consider, I will consider a little bit more general probability, which I will also call gap probability, although it's not gap at all. So if you consider the indicator of the event that you have a system of interval delta 1 and so on, delta k, and also the system of natural numbers in m1 and so on, mk. And you consider the event when the number in the interval delta 1 scaled like this. You have just m1 number. In the interval L2 you have just delta 2 you have just m2 and so on. In the cut interval you have mk interval. Of course, this could be written, this indicator function, but the formula is not so short, so I just write how it looks in the case for m equals 0. For example, if you want to consider here, this is the indicator of the event that the interval delta is empty, and if you want to know what is the indicator in the case when interval delta contains k points, then of course you have to consider the sum over all subsets of 1 n such that norm E is m, and here you should write the product 1 delta of lambda j for j from this I, and product 1 minus 1 delta lambda j for j does not belong to And if you have more intervals, something like this, but I don't want to write formula exactly, it's not so important. It's important to have that it is a bounded function of our variables. So, and in this case, universality means that if you consider the expectation of such indicator function, which of course is the probability to have this event with respect to our probability measure, then, and take the limit, then the limit becomes universal, and it will become universal means the same, that it does not depend on v and does not depend on the point lambda 0. And there is one more kind of universality. There is a way to consider, okay, in some sense, it is the same as the second universality, but because they are equivalent. But if you consider the generating functional in this form, you take any function phi, which is, okay, stepwise continuous and bounded from 0 to 1, and consider such a product, then the statement about universality means that this functional, after expectation of this function, in the limit when n tends to infinity, becomes universal. And I will consider all the 3 points when I will speak about universality. And what I would like to say is that, in fact, universality was studied very well for beta, for matrix model, was studied very well for beta equal 2 and a little less, but also well enough for beta equal 1 and 4. And in all these cases, it was possible to prove that there is a limit pointwise of this correlation function. And if you are able also to prove that this limit is uniform with respect to S1 and so on, Sm, then you can integrate and obtain this gap probability. And it was surprised for me, okay, maybe I am stupid, but it was a new idea for me, that it's possible to consider from the very beginning the indicator of the set which you are going to find probability of, and to prove that it is universal. And I took this idea from the paper of Valko and Virac. Okay. So I would like to also to say that the result about universality is not new. The result about universality in this form a little bit weaker that it is written here. The first one was obtained in the paper of Erdős-Yao and Bourget in a number of papers between 11 and 13. So the new is the methods, and maybe it's new, these results, but I'm not sure. I'm not sure about it. Is it a new work or not? And I would like to apologize because I will mention in my talk, I will mention only result which I need to use. So the complete references I can give after if you want. But now I will mention only a few results which I will really need to explain something in my talk. And at the end, I will compare the results of the paper of Bourget, Yao, and Erdős with my results, and maybe say a few words about this. Okay, so to formulate condition, I need to know what is the equilibrium measure. To explain what is the equilibrium measure, it's a typical problem of the complex analysis. You have logarithmic energy, and you consider this energy problem when you have to find minimum of the functional written here with respect to all unit measures, all possible unit measure. And it is well known that for any continuous V, the problem has a unique solution, which usually called the equilibrium measure M star. And it's also well known that if V prime is a Hölder function, then this M star has a density without star, which is with a compact support, and the density rho will be, I will refer as an equilibrium density. And okay, I also need to say a few words about this. Is a necessary and sufficient condition to have some density rho as a solution of your equilibrium problem. It's written here, so you have to construct this function, and it should take its maximum only on the spectrum. And it's less or equal to v prime, and I have written this condition only because of the fact that I need to say that if I will speak about generic behavior, it means that here cannot be equality, only inequality. Okay, the first step which I need to mention, the first result which I need to mention, which is really important for all these methods, is the result, very old result of both Emmanuel Pastor and myself. It was obtained also by Johansson, but okay, the difference was that there were not, in the Johansson paper, there was no the bound between. Just it was proved that there is a limit for this, and there was no this bound and there was no this bound, you know, because here is the bound for the convergence of the integrated correlation function, which is important. By the way, in his paper, Johansson used this bound taken from our paper. Okay, and the second result which I would like to mention is the famous Johansson paper of 98, where he proved that if you consider the small perturbation of your potential, if potential is one cut, which means the support is one interval, and if you add this small perturbation and consider here, if you consider the behavior of this, then the answer will be that you obtain some quadratic form with respect to this perturbation h, and this quadratic form could be written like a quadratic with some operator d sigma, which depends only on the interval, doesn't depend on potential v, so it also is universal. And here the measure nu could be found from this equation, but in fact I will use this theorem only for Gaussian case. In the case of v equal to lambda squared divided by 2, so this term will disappear because the polynomial p written here is just the coefficient in your equilibrium density, and if you have Gaussian case, then the equilibrium density has here 1. P is 1, so here you obtain 0. So in the case when which I will describe, in this case, this term will disappear. And what I will use and what is for me interesting that this one, any number, positive, any positive number, yeah. Okay, so what will be important that if you consider this d sigma, it is just rank 1 perturbation of L sigma. L sigma is an operator with integral operator with logarithmic kernel. So if you multiply this by this, you obtain 1 with rank 1 perturbation. Okay, and the last result which I am going to use is a result about so-called large deviation, which is very convenient if you want to study matrix model, and the statement is the assertion is the following. If you restrict in all your definition, if you restrict the integration by some epsilon neighborhood, sigma epsilon, of your limiting spectrum sigma, then nothing will change. In fact, that the bound will be of order e minus n some constant. So you could restrict yourself only by integration with respect to sigma epsilon on the real line, and your mistake will be of this order, very, very small. So outside of this interval, you can change your potential as whatever you want in any way. Okay, so starting from this moment, I will assume that all integration in my talk will be with respect to this sigma epsilon neighborhood of the spectrum. And now let me begin to explain what is the result. In fact, the idea is also not new, because the change of variables was widely used by physicists, for example, to derive loop equation. The first loop equation is a very famous thing. All people who worked with matrix models use this loop equation. So the difference with respect to the methods, normally to derive the loop equation, you have to consider some transformation of variables, which is unit transformation plus epsilon something. And then you can consider the first term with respect to epsilon and obtain some equation which normally called loop equation. And what I do, I did not consider, what I did not consider this case 1 plus something small, but I considered general type of transformation, any possible transformation which is smooth, transformation of the interval sigma epsilon to sigma epsilon, such that you have, okay, the derivative positive. And of course, you can consider, if you do this transformation, you can obtain the new Hamiltonian. And here, okay, here I just put instead lambda zeta of lambda, and here also. And this term appears because of the integration. And 2 over beta is here because I multiply, when I construct the Gibbs measure, I multiply by beta over 2. So 2 over beta just to have 1 after multiplication of beta over 2. And it is evident, of course, that if you consider the partition function just the integral, you obtain the same. And if you consider the correlation function, you obtain, okay, correlation function, but in different points. On the other hand, you can consider your Hamiltonian, if you want to come back to your initial Hamiltonian when you have interaction term, I mean logarithmic interaction, written in a normal way, you can write it like this. And so do plus and minus this term. Here is plus and here is minus. And I add here I is not equal to j, and here I add this term. Then you have log of derivative, and I subtract it here. Because initially it was written I is not equal to j, and now the sum is without this restriction, but when I is equal to j, of course you have to subtract, you have to add log zeta prime, and I add here and I subtract it here. And now what we have, again, some potential, logarithmic interaction, and some pairwise interaction between different points, and this pairwise interaction is a good operator, smooth. Okay. From here, because if I want to have the same integration, I should multiply by the derivative. And I put this derivative in the exponent. But since the measure should be multiplied by beta over 2, then okay. And you have this kernel, which is very good smooth kernel. And for future, it is important to write it as a difference of some positive operators. And of course, here you have freedom how to write. The most natural way to do this, just to take the positive definite and the negative definite part of this kernel. And the initial version, it was written like this. But after I understood that it's more convenient to take some another positive operator, which are also smooth. Of course, in this case, okay, I shall take some L plus and L minus, which is not the positive and negative part of this operator, but something which I can construct. And what in fact, I need not to know that it is positive and negative. I need to know that there is some inequality for this, I mean, this first operator. And okay, the kernel should be smooth. And if you consider for sufficiently smooth zeta this operator and the eigenvalues and eigenvectors, then you can take eigenvectors and eigenvalues of the first one, and then with plus, and eigenvalues and eigenvectors of the second one with minus. And of course, you can construct the common system of vectors which will not make the basis in your space. It will just some system of vectors in your space, but I will not use that it is a basis in the space. What I need only to know that here is a uniformly convergent series with respect to K. So I will construct this system of phi k and psi k and eta k as an interlaced system from this and this eigenvalues and eigenvectors. And of course, if both operator has smooth kernel, I will have uniform convergence without any problem here. Okay, and when I constructed this, I can explain what is the choice of the function zeta. Very simple. You just take zeta prime equal to the ratio of the semicircle density, which standard semicircle density, and your density, equilibrium density, which you obtain for your potential V, and put initial conditions that zeta of -2 equal to -2. And okay, if you, since you know, of course, there is a special point when lambda equal to 2 and -2, but the ratio is, because both functions have zeros in the numerator and denominator. Okay, you cannot use standard Picard theorem, but you can use, okay, some modification of it and put in half of pages that there is a solution of this equation. It is unique. If you put these conditions, then you obtain that zeta of 2 is equal to also. And you can write, you can extend this solution on sigma epsilon with the same number of derivatives which they have inside the interval, and this number depends on the number of derivatives of function p, which appear here. And the most convenient way to write, in fact, this equation is just like this, but it's more convenient to write like this. So if you have this, let me write what I have in my Hamiltonian. I have the sum of L zeta, and of course, because of this, I have this equality, and I can write it like this. Here I just subtract and add this term, the integral of my function, which is smooth with semicircle density, and I obtain this term, which I call R of lambda. It's something like pairwise interaction, and here is written the linear term because it depends only on lambda j, the dependence of lambda k disappear, and here is written just a constant, some constant. And what is important, why I choose zeta of lambda in this way, then if you compute this term, you obtain v of z of lambda minus lambda j squared over 2. And here is just the difference of the energies. So your Hamiltonian will take the form with this choice of zeta, will take the form you have Gaussian, you have interaction, standard logarithmic interaction, you have some small perturbation, you have this atom, and this is just a constant. Okay. The next step is just, okay, I don't want to have this R, I would like to linearize it, and there is a standard way in statistical mechanics how to do, maybe in analysis. In statistical mechanics, it usually called the Hubbard-Stratanovich transformation, but it's just Gaussian integration. So for each, okay, I forgot to say, now I would like to restrict summation by m, where m could be any. In fact, all the bound which I will obtain below doesn't depend on m, so I can restrict by some m, and after obtaining the bound which I will need, just to send m to infinity. Because all bound will be uniform and doesn't depend on m. And I would like to write the term like this, like just a Gaussian integral with respect to, it's not written here, sorry, but this integral is with respect to uk. The k integral is with respect to uk. And then if you denote this guy like hu of lambda, it's of course function of lambda and also function of uk. It depends on uk linearly. Then, and one more notation which I will use, this is with dot means that I subtract the expectation from here. And so what we obtain, I obtain, for example, in the global regime, if you want to consider what is the ratio of the partition function, then you obtain immediately that it is this constant, and then the integral of this guy with respect to du. And of course, it's not written here, but the limit when m tends to infinity. Okay, now let us consider what happened here. Here we have just the generating functional of the linear eigenvalue statistic, which you can consider according to the Johansson paper. And using the Johansson result, you obtain, instead of this, you obtain this guy, and, okay, sorry, I forgot again the right. So there is also the term which with nu, the measure nu. And this guy is just a quadratic form with respect to u, because hu was linear, and after it was uk was multiplied by psi k when you apply some operator and then take the scalar product. Of course, you obtain something which is quadratic with respect to u, and you have to care only about this integral. If it is convergent, then you can compute whatever you want without any problem. And of course, if from the very beginning you have some additional additional perturbation, if you want to prove Johansson paper, for example, the result of Johansson paper, you just have to add here, not instead hu, in the place of hu, you should place hu plus something which doesn't depend on u. And you obtain, then you again use Johansson result only in the Gaussian case, by the way. And the proof in the Gaussian case is, okay, trivial completely with the proof of Johansson. Use it, and if you know the term which contains nu is not important, it is linear with respect to u. What is linear does not have some influence on the convergence of this integral. And here you have to choose that the integral will be convergent. This is the only important place in this theory. And okay, if you want to study local bulk regime, you can do in the same way. When you do the change of variables, your system of, and you consider your indicator, it becomes again the indicator, but indicator of the another set. And this set, if initially it was interval for delta j when lambda between lambda 0 plus aj over n rho, and here L0 plus bj over n rho, then you should replace this interval by the interval when zeta of lambda are between this, and of course you can apply the inverse transform, and you obtain that lambda is between this, in your new system, the lambda between these 2 points. And for example, if you want to consider this left-hand h, you obtain that it is zeta of lambda 0 plus this guy, and zeta prime will give you the ratio of the density. So you will have right normalization here, because zeta prime, I just recall that it is, it was the ratio of rho semicircle by rho this one. And so you obtain the system of interval of the same time, and this term which is of order n minus 2 could be easily controlled, so you really obtain the same situation. And in the case when you consider the universality of correlation function, it suffices to consider the system of correlation, the system of function constructed like this. You take some family of smooth function with compact support. You construct this scaling function, take a sum divided by n, and then construct the product. And if you are able to prove that the limit for any such a function is universal, then of course you obtain the weak universality of the correlation function. But I will explain in the following, I will explain the idea of the proof for gap probability for this indicator function, because for indicator function it's more simple, in fact. They are bounded from the very beginning, and you have less troubles with this. Okay, and then in the case of the indicator function, you obtain that you should study the integral like this. So you have almost the same that you have in the global regime, but here you should multiply by your deformed indicator function. And okay, here it's written the same just by adding and subtracting the term. So you obtain this, and I add, and here I add, and here I subtract the same term. And since E1 is the normalization, En minus 1 is the normalization constant, then this I can put outside of the integral, and this guy integrated with this will give me exactly En minus 1. So, and now the problem is just to prove that this and this is the same. The difference is small. And I would like to stress here, to mention here, that what we obtain for free without any calculation. You obtain that it is enough to prove, because here you see, here the expectation is with respect to Gaussian case. And you have only this small perturbation field. So if you are able to prove that this small perturbation field does not imply in the behavior of your function, so if you are able to prove universality for Gaussian case with a small perturbation, then you are able to prove universality for any potential. And how one can prove the universality in the case of this small perturbation? The idea, again, the statement is that if you add this small perturbation and divide, okay, before it was written like a product here, but if you want, better to study the ratio to be sure that it is small. And so if you are able to prove that this difference is small, then you can prove universality without any problem. And how to do this? In fact, the same idea. Let us apply this change of variables once more. Now we have potential V star, which is the Gaussian potential, plus small perturbation. It's a new potential. Forget about this 1 over n. It's not important that it is small, but let us construct the same transformation for this new potential. But there is one problem. The problem is that construction is based on the fact that the equilibrium measure have the same support for your new potential. So it needs from the potential, from this field H, you need to have two conditions. There are two integral, one to provide that singular integral equation has bounded solution, and another one to provide that the density will be 1. I used both these facts in the proof, in the construction of perturbation. And that is why I need to consider not my field itself, but something which is a little bit different. I consider some quadratic function and choose coefficient A and B to provide these two conditions. There are two conditions. They both linear with respect to H, in fact, linear with respect to H prime. And from these two conditions, I can find A and B, this function f. A and fb I don't want to write because they are rather complicated, but it's not so important. It's important that they do not depend on H. Some function independent of H. And so for this potential, I construct this L in such a way to provide conditions that I can use my strategy of change of variables for this H tilde potential. So for this potential, I can construct my zeta H, and of course it should be like this. It's very easy to prove. And then if you would like to construct the corresponding integral operator kernel, you obtain that it is like this, log 1 plus over n, and this guy is bounded, smooth, and so on. And in this situation, in fact, I will call, you remember this R. R is just this one. But when eta k are of order 1 over n, you have something like this. Here you have additional n comparing with the first case. So you need only to prove that this tends to 0. In fact, there is a very simple way. You can just use, for example, to put parameter t before this r and prove that the function which appear here tends universally with respect to t to 0. And for this, you can just to compute the second derivative, the first will be 0 by construction, and the second derivative you can bound by using Braskamlin inequality, for example. Because your system now have convex Hamiltonian, because this is something small comparing with your Gaussian plus logarithmic. So you have convex Hamiltonian, you can apply Braskamlin inequality, and you can bound your derivative without any problem. So this is simple because, okay, if you know this, of course you can prove this because this is bounded. You can just apply Cauchy inequality and prove that it tends to 0. That is why it is very convenient that it is bounded. And by the way, that is why the function phi for correlation function written in the way which I can use also for which I can use also the Cauchy inequality in this case. It would be a little bit more complicated, but in fact the idea is the same. Okay, and so you obtain that this is small, and so what you obtain, in fact, you obtain that you remove H tilde potential, but you left with this L potential, which was quadratic from the very beginning, this L, which I constructed here. Okay, and to remove this potential, I use the corollary from the result of Volkov-Virac 0,9, because here is just for Gaussian potential. I need something exactly for Gaussian potential. And it follows from the result that if you consider this probability, gap probability, and you shift it by something which is small comparing with 1, t should be smaller than n, then in the limit you obtain something which is tends to 0 when n tends to infinity. This is just the place where I need this. By the way, in the first version of the paper, I thought that in the paper of Volkov and Virac, it is proved the same statement for the correlation functions. I was mistaken. That is why it was in this sense, it was mistaken, my first version of the paper. Okay, and now if you use this, then you obtain the statement of your lemma for the indicator function without any problem. And as for correlation function, you cannot remove L, and you obtain that you can use the same procedure, but you obtain in the limit that you should to consider the expectation of the function like this. And this t of h is proportional to h with some function, just linear. Okay. And lemma 1 was for real H, and now there is very standard way to extend the inequality on the complex H. We need this for complex H because our integration in our field could be complex. It's just some modification of the very well-known theorem of complex analysis about two constant. If you have two constant for harmonic function bound on the part of boundary, you have one constant, and on the another part of boundary, you have another constant. Then you have something in the middle for harmonic function, and I use this modification written here. It's not very important, but just few lines from complex analysis to do this. Okay. And now I'm ready to present you what I obtained in this way, and the main result for one cut is if you have, okay, now it's 7 derivative, maybe it will be less a little bit, maybe 6, I'm not so sure. With 7 I am sure, but with 6 not so sure. Okay, then you can prove universality of the gap probability. Here, using the result of Falco and Virac, you obtain 0. You can prove the universality of generating function with any stepwise continuous function phi. You remember it was construction, the product 1 minus phi of lambda j, what was psi phi. So this universality you can also prove. And here you obtain some additional integration which appear because of the term dependent on L. After integration with respect, because you have, if you put instead of your LH, you put LHU, you obtain something which depends linearly of u. If you integrate with respect to lambda, you obtain some fixed vector in your u space. And integrate, you can integrate with respect to extra direction, orthogonal with respect to this chosen one, and then you obtain some additional Gaussian integration. So, sorry, but now only this form. And okay, for multi-cut potential, you can do the same. Here it is written that V is real analytic, but it's just because I need to use my previous result about multi-cut case. And in this previous result, it was proven that when you have multi-cut potential, you can consider some similar transformation and make it like a one-cut potential plus some additional field, small perturbation. Then if you use this, then you can use theorem 1, so it's just 2 pages to extend on the case of multi-cut potential. And okay, it could be also proven. No, in fact, in all proof, you don't use what function you have here under integration. What you need some boundedness and the existence of the limit for your Gaussian case. And so the proof is exactly the same if you take real analytic, for example, multi-cut potential and consider any h point, and you obtain that in the limit when n tends to infinity, you obtain the same gap probability, the same indicator function, limit for the indicator function as in the Gaussian case. And for this, instead of the result of Valco and Virac, you have to use the result of Edelman and I don't remember the second one. The second was, sorry. Okay, and I would like to compare the result obtained before me by Bourget, Erdős, and Yao. And here you see that less derivative. For derivative, I cannot do this for derivative. I need more, definitely. But here is some additional averaging. Okay, I have also additional averaging. By my averaging is over the interval of the length comparing to 1, because Gaussian integral is, in fact, the integral of the, it becomes small if you have your variable big. And here is the averaging with respect to the interval, uniform measure of the interval, which is big comparing with 1 over n. So in this sense, it's my result a little bit, not so much, but a little bit better. Okay, and the similar result we obtain in the paper in the same paper. There is also, you know, I know that Alice make a talk in the previous conference here about similar results of Guéhenné, Figali, and I don't remember, Beckerman, something like this. Beckerman, in fact, okay, they have, first of all, it is the third result at the same direction. And again, they have averaging, but even not like this, but there is averaging with respect to the whole interval in their paper. So in this sense, again, my result is a little bit better. Okay, thank you. That's all.